Hello everyone. Our topic for today is about a moment of inertia. So first, when you are to Google the term inertia or the word inertia, the definition is according to Google, it's a tendency to do nothing or to remain unchanged. When you see it closely, it is more likely synonyms to the word resistance. So inertia is resistance. And what about moment? In physics, when you heard about a moment, the first thing that comes in your mind is the unit, like the Newton meter, kilonewton meter, pound per feet, or pound per meter. So basically, moment is the product of a certain force and its perpendicular distance to a certain point. So when you have here when you have a force here and you want to analyze this point here, so that would be your force, and this it will be perpendicular to the force right here. So the product of your force and the distance right here, that will be moment. So for example, when you apply a moment to a non-static object like propeller, so when you have a propeller right here, for example this will be your propeller, and you apply a moment here, the tendency of the body or the tendency to this propeller, it will be rotate or rotation. What about when you apply a moment to a non-static beam? For example, this will be your beam, and you apply a moment right here. So the tendency of this moment, it will bend in this manner. So your beam will bend like this. So what about when you apply a moment to a cross section? So for example, you have a cross section right here and you apply a moment right here, the tendency for that this cross section will twist. So basically our topic for today is the moment of inertia in resistance to rotation, bending, and twisting. So there are three major types of moment of inertia. The first one is the mass moment of inertia. The second one is the area moment of inertia. The third one is the polar moment of inertia. The mass moment of inertia is the resistance to rotation, and the area moment of inertia is resistance to bending, and the polar moment of inertia is resistance to twisting. So we'll just tackle these two right here, the area moment of inertia and the polar moment of inertia, because this one is under statics, and right here is under dynamics. So area moment of inertia is denoted as I. So when you were asked to solve for the moment of inertia in terms of x, so the general equation for that will be Ix is equal to the integral of y squared times differential area, where your y squared right here is the distance from your x-axis, so this will be your y, distance from your x-axis to your differential area. And when you ask to solve for the moment of inertia in terms of y-axis, so the formula for that is x squared, integral of x squared times the differential area. So the distance from the y-axis to the differential area, that would be your x. So I have a certain shape right here, rectangle, triangle, and a circle. I have its formula for the moment of inertia. Rectangle is equal to Ix equal to base times height cube over 12. So this formula right here is derived from the formula that we have earlier, the general formula. Ix is equal to the integral of y squared times the differential area. So either of the two, you will come up with same value or answer. So just take note that this formula right here is the moment of inertia about to their centroidal axis. So this is the y-axis here, and this is the x-axis here. So how about when the x and y axis is not on the center of the object? So we will be using the formula, the transfer formula for moment of inertia, and that formula is transfer formula for moment of inertia. So that formula is Ix is equal to your centroidal, or the moment of inertia of your centroidal axis. So let's denote that as Ixo plus the area of the shape, rectangle or triangle or the circle, times distance squared. So this d right here is the distance from your centroidal axis to your axis, or the chosen axis right here. So this will be your d right here. So I have a sample problem right here. Determine the moment of inertia about x1, which is located at the top of the vertex of the triangle, if the base of the triangle is 50 millimeter and the height of the triangle is 60 millimeter. So the first thing we need to do is to first calculate the moment of inertia on the centroidal axis right here, the x sub o. So the formula for the centroidal axis moment of inertia of a triangle is base times height cube over 36. So let's just do direct substitution. Base is equal to 50 times 60 cube over 36. So the total for this moment of inertia for the centroidal axis is 300,000 millimeter 4. Now to solve for our moment of inertia about the x sub 1. So as you remember, the formula is Ix sub 1 is equal to the moment of inertia of the centroidal axis, the Ix sub o, plus the area of the shape times the distance from the centroidal axis to your chosen axis, or the x sub 1 squared. So we'll need to find the area of the shape first. So the area of the triangle is equal to 1/2 times base times height. So that would be 1/2 times 50 times 60. So it is equal to 1,500. So now we need to find our d. There's no given for the distance from the centroidal axis to your x sub 1. So as I remember to the previous lecture that we have, this right here, from the apex to the center of the triangle, it is 2/3 times h, and this is 1/3. So this is our d right now. So d distance is equals to 2/3 times our height, which is 60. So the distance from the centroidal axis to your x sub 1 is 40. So now we can solve for the moment of inertia about x sub 1. So from the formula, the moment of inertia from the centroidal axis, which is the 300,000, plus the area of the rectangle, which is 1,500, times your distance, that's 40 squared. So the total for that is 2,700,000. So that will be your moment of inertia about x sub 1 millimeter. This will be our final answer.